In this video, I'm going to summarize the layout of static and dynamic arrays on the stack and the heap. And to do so, I'm going to review the code that I presented in the reading, static-dynamic.c. And first, I want to show the static allocation, just to review. We see that there's 4 elements. For the dynamic memory, we have 4, and it's got to be a long unsigned int. We cast the void pointer returned by malloc to make it an integer pointer. And then we have to individually allocate these because it's dynamic memory. The next thing we do is we print out the addresses of the static and dynamic memory. Now in the reading, what I showed you is that there's this concept here where they print the same address on the stack. Now here's what I mean by this. In the dynamic memory, the base address is a register, and this points to a location on the heap. It's dynamic. Since it's static memory in this line of code, what this means is that we know exactly how much memory is being allocated. It cannot be reallocated, and therefore the operating system knows where it is. So therefore, if I print the address of int static and int static itself, they actually print the same result. And if you see here in the reading, they will print the same result. When I compile it again, it's going to do the same thing. So that is a crucial difference in how static and dynamic memory work. So we need a pointer to be able to access dynamic memory, and that's a crucial concept for you to be able to succeed in this course and as computer scientists and engineers. For the rest of the code, I iterate through and I print out the value and the address for static and dynamic memory. So here it's a static value and its address, then dynamic value and its address. Now I did this deliberately. Notice how the 4 elements are 10, 20, negative 19, and 34, and dynamically they're 10, 20, negative 19, and 34. So even though the data is the same, the structure of the arrays is different. And then finally, I free the dynamically allocated memory. Now I'm going to uncomment this on my second compilation to show you what happens when we statically allocate memory. So I'm going to compile this code here. So there's the compilation. And we now see the specific output. Now what I'm going to do is I'm going to copy this result, which is actually different addresses than the one you will see in the write-up. It's allocated every single time for different compilation. And I'm going to show you how to translate what we have here into the drawing that I presented in the reading. So first I'm going to say the stack, and I'm going to say registers, and then I'm going to say heap. So the first thing we're going to do is we're going to say where the base address of all these elements are. As I've discussed in the reading and just now in this video, these 2 addresses are the same. So we're going to see here that the base address of the array on the stack also contains the value 10. The base address for our dynamic memory is the address in the register. And I'm going to say that this value is what's stored in that register. So it is there in this register, and that address, as we see here, matches the base address on the heap. And that also equals 10. The next thing we need to do is we see that there's an offset of 4. So let me bring this back here, and that equals 20. And then here also has an offset of 4. And that also equals 20. We now have another offset of 4 since it's an integer, and both of these are going to be negative 19. And in fact, I could just copy this and add 4, and I'll know where the address should be. That's going to be 8, and we confirm that's the case, and that is also negative 19. Oh. Huh, interesting. All right, cool. That solve that formatting issue. And then finally, C, remember 8 plus 4 is going to be 12, and that's C in hexadecimal. and that's going to be 34. And the same thing, this will be 0x12 echo 901C. We see that that is also 34. So what's the crucial thing here? What are our takeaways? Well, we have a register. They are fast and limited, and this is pointing to the base address on the data heap. When we perform malloc, we allocated this memory, and that's the layout. In the stack, because we know how much we have at the beginning, and there's no reallocation, the operating system knows where this is going to be. So therefore, we can do this specific layout, and we can access all of the data. The other crucial thing to take away is the difference between data, see we have the exact same type of data here, and structure, because the heap and the stack allocate the structure of that data in two different ways. Finally, what I want to do is I want to uncomment that free static dynamic.c. So let's see what happens when I uncomment this. What's going to happen here? Well, we're trying to free dynamically allocated memory, and we see that we get an error. This is one of the reasons why I insist that we have the production quality compilation flags. But let's say we want to get rid of these, and we are going to allow ourselves to break the program. So it's giving us a warning. Attempt to free a non-heap object. Well, what's going to happen? We see that we get one of those memory maps just like we had earlier, and the reason why is we're trying to double corrupt. We're trying to free memory. And we see here, if we go to our code, we got a core dump. And what a core dump is it's trying to release memory. And the thing is, with static memory, once we're done with it, it's automatically freed by the operating system. So what happens is, that is why this particular error message says double free, because we tried to free it twice. And we see that the base address here, 7FF echo echo 8F679, I'm sorry, this one here that ends with 67920, we see that it tried to free 67920. So we tried to free a memory that was not on the heap, but that's already done by the operating system. If you do it twice, you'll get this memory map.